So let's consider, we know from before the Hall effect that if we have magnetic field, we have current flowing through here, that it's going to produce a voltage across there. Well, let's look at this a little bit more also. So in that case, we got the magnetic field that way, but what if instead we had a magnetic field to the right and we had a current, like a wire with a current flowing through it that way? Then what happens? Well, the forces are going to be acting on the charges going through there, and so we're going to have forces on it from the magnetic field. So that means that we want to find out, well, what's going to happen. Well, if we have electrons and they're going down, then the right hand rule would be that would be into the board. Right hand rule says out of the page, out of the screen, but because they're electrons, they go the other way. If it's positive charge going up, right hand rule would indicate also inward. So either way, it's going to be inward. Okay, and so the force is going to be perpendicular to the wire. Okay, you might initially suspect you might get a voltage across there, the Hall effect. But you're still putting a force on that wire. So even after you balance things out with the individual charges, the magnetic field is still exerting a force. And so that means it's going to push on the entire wire. Okay. So if we're pushing on the whole wire, then what's going on? Okay. Well, we know that the magnetic force is QV cross B. So if we look at the individual charges in the wire, so we got a wire here, and we got the individual charges moving, the force on each charge would be equal to, we're assuming, the perpendicular, so let's make an assumption that V cross B is just going to be V times B. Okay, and that's perpendicular. So we'll assume that the magnetic field and the voltage are perpendicular to each other. So that would be QVB. Well, what V? Well, the average velocity would be the drift velocity. Okay, and so Q, that's the charge. Well, how much charge is actually moving in the wire? The amount of charge moving in the wire depends on how much current is in the wire. Now remember, current was dq dt, but we also derived that for a wire that we could also say that the current is going to be equal to Q times V sub D times, or rather divided by L. Okay, so in other words, Q over L, so it's the lambda. Okay, so if we plug that in for Q right here, so F equals Q V sub D B. So plug that in for Q, that's IL over V sub D times V sub DB. The V sub drift velocities cancel, and so the force on the wire is IL times B. Now the way we normally define that, because clearly if magnetic field is this way, if the current is going that way, we've got a force. Okay. We already said that would be a force into the screen. On the other hand, if B is to the right, but if I is down, that's going to be a force. So in this case, force is in this case, force is out. So what if B is this way and the wire is running that way? So I is that way. Well, it turns out that if you're moving parallel to the magnetic field, you don't get any force. So there is no force there. Okay. And so in that case, there's no force. Likewise, if I was that way, there'd be no force. So other sort of options here. What if B is like that and we have a wire that's going inwards like that? Okay. In that case, right-hand rule, the force is going to be down. Okay. What if, on the other hand, we had I coming at us? Okay. In that case, the force is going to be up. So what do we get from all this? Right-hand rule. I cross B. Well, unfortunately, and I think this is kind of a dumb idea, we normally define the current to be a scalar rather than as a vector. So we gotta have a vector involved. So we say the force on the wire is I times L cross B, where L is a length that is in the direction of the current. Okay, so again, I think this is kind of a silly idea, but that's how it's normally defined. L is a length that's in the direction of current. So we don't define the direction of the current. We define the direction of the length as the direction of the current. So not my fault. I didn't come up with this. I'm just telling you what the book does. Okay, the book does it like everybody else does it. But this is now a force on a wire.